Hello, hello. We are back together again, and we're continuing our adventure in volumes by cross sections. We're just, going to get more complicated with it today. Example 1, we're just diving right in here. Set up an integral expression to find the volume of the solid whose base is a region bounded by that circle there, x squared plus y squared equals 16, with cross sections taken that are perpendicular to the x-axis. They are isosceles right triangles with the hypotenuse lying on the base of the circle. Okay, so that's where my cross section is going to be. And then there's my isosceles right triangle. So this one's a little bit tricky because if I take this function right here and I solve it for y, because we're parallel to the x-axis, so I'm going to solve it for y, I get y equals plus or minus the square root of 16 minus x squared. Well, the plus part of that is on the top half of the circle. So that's only half of the hypotenuse down here. And then the negative version of that is on the bottom part of the circle. So that's the rest of the isosceles right triangle. So then the base of my isosceles right triangle is 2 of the 16 minus x squared. So pause the video if you need to and let that sink in just a bit. So we're going to drop a height on this so that we can find the area of the triangle. So 1/2 base times height. The height is root 16 minus x squared. So that means the area is 1/2. There's the base and the height. And if you're wondering where this height came from, go watch the part 1 video of this series and that'll make sense to you. So clean that up a little bit. We've got 16 minus x squared is the area. Okay, so now we're going to integrate this thing to actually find the volume, but what would my bounds be? The circle has a radius of 4, so my bounds are going to be -4 to +4. So there we go, stick in the area of the circle. Now another thing you could do is, especially if you're doing this by hand, you could take the bounds just from 0 to 4, just take half of the circle and double it in the end. Because when you're evaluating, 0 is just a lot easier to plug in. Let's try another one like this. R is the region bounded by the graphs of x equals y squared and x equals 10. Find the volume of the solid that has R as its base. All right, every cross section is a semicircle and perpendicular to the x-axis. Okay, so we have a semicircle perpendicular to the x-axis. And the top part, just this top part right here, that is going to be the square root of x. And then the bottom part is the negative version of that. So my semicircle, the base of my semicircle is 2 root x's. Okay, now the area of a circle is 1/2 pi r squared. But this is cool because r, again, is just half of the diameter. So r is just going to be the square root of x. That's all we have to deal with for the radius. So that's not too bad. And then you can just clean that up a little bit and you get 1/2 pi x. So that's the area of our semicircle, and now we're going to have to integrate that. We're perpendicular to the x-axis, so we're going to go from 0 to, well, 10. That's where they told us we were going to stop. And then just plug in my little semicircle area. If you want to clean that up a little bit, you can get pi over 2 x dx, and we are actually solving this thing, aren't we? Okay, so we'll take the antiderivative. And evaluating that from 0 to 10, you get 25 pi units cubed. Set up an integral expression to find the volume of the solid whose base is the region bounded below by the lines x plus 2y equals 6, x equals 0, and y equals 0. The cross sections are perpendicular to the y-axis, and we have equilateral triangles. All right, so if the cross sections are perpendicular to the y-axis and they're equilateral triangles, that's fine, but because they're perpendicular to the y-axis, we need to take our line here and solve it for x so that the line is in terms of y. And now we know the length of this cross section is the function 6 minus 2y. So that's the bottom of our equilateral triangle. And that means that the height is going to be root 3 over 2 times that. The area of my triangle is 1/2. There's the base, there's the height. Clean that up and you get root 3 over 4 times 6 minus 2y squared. Now we're going to have to integrate that, and if we're working with the y-axis, that means our bounds of the integral are going to be our y bounds. So that's going to go from 0 to 3, and we can pop in our area. Buckle up for this one. This one has some little craziness to it. Let R be the region bounded by the graphs of y equals x squared and y equals 2 minus x squared. We're going to set up an integral to find the volume of the solid. Every cross section is perpendicular to the y-axis and is a rectangle with a height of 3. That's what we have so far. All right, now notice for just a minute, this cross section here is only touching the y equals x squared function. And that holds true all the way up until it hits that line y equals 1. And then above the line y equals 1, it's only hitting the function 2 minus x squared. So we're actually going to need two integrals here. The first integral is going to be from y equals 0 to y equals 1. And that's just the blue function. So let's figure out the area of that. If we solve for x, since it's perpendicular to the y-axis, we get x equals plus or minus y squared. So there's a positive length of that and the negative length of that. So the base of my rectangle is 2 root y, which means the area of that rectangle is 6 root y. So there's the volume for the bottom half of that. And now working on the top half, we're going to go from y equals 1 to y equals 2. If we solve for x, you get plus or minus the square root of 2 minus y. We're still working with rectangles. And so the bottom of that one is going to be 2 times the square root of 2 minus y. And the height is still 3. So the area of that one is 6 times the square root of 2 minus y, and then pop that into the second one. And there is our integral expression for the volume of that thing. That'd be interesting to see in 3 dimensions. Example 5, last one. Let R be the region that's bounded by f of x equals e to the negative x squared. That's the one on top. And g of x equals 1 minus cosine x. That's the one on the bottom. Find the volume of the solid formed whose cross sections are quarter circles that are perpendicular to the x-axis. Let's start by finding the x bounds here. Where do these two functions intersect? So thankfully this is a calculator question and you can let your calculator work that out for you. Plus or minus 0.9419. Now the tricky part, find the area of the base. So I've dropped a cross section there, and that pink line is the bottom of a quarter circle. Okay, so how long is that line? Well, it's going to have to be the top function minus the bottom function. The area of a quarter circle is 1/4 pi r squared. Okay, so there we are, 1/4 pi, and then here's my r squared. That's really long. And then finally, we just have to write the integral. We know the x bounds and we know the area. So boom, just put that into an integral and let your calculator do the heavy lifting on that one, and you get 0.7242 units cubed. So that's the end of cross sections. I hope it's starting to make a little bit of sense. If not, hey, this video is always here for you. See you later.